Cool. So this should be a short thing. And just a couple of things came kind of together that I thought would be interesting to do a quick video on this. So it's about quantum error correction, and it's not going to be here some sort of like theoretical whatever. It just kind of realized I realized I found the Shor code, which I didn't know about before. I knew about the idea of encoding it in sort of entangled states and then using the party, right? I think something like that, right? But then, because I stumbled upon these blog posts from Agent Anarchy in AI, which basically it's I think it's older, and I think it's trying to use that code and mix it up with quantum teleportation, but I think he's not using it the right way. But I mean, it doesn't matter. He because I basically he said that he realized that something that belongs to lower layers in the stack, which is what he says in his response in here. Which kind of sure, it's a bit it's one like that makes sense, right? Because it's not something you do at that level. It's something that you do to encode logical qubits. Nevertheless, I thought it would be interesting to just play with the circuit and um, see what the properties are of the circuit. So the idea is, that this circuit in principle should help you fix both bit flips and phase flip errors that might happen in this box E, right? So the way this is used in Anakin in Agent Anakin's block, it's I think he's trying. Let me see if I can zoom in. I think it's trying to kind of because this is definitely so. This is definitely the error correction part, and this is the same, but it's kind of flipped because I think he takes that state in here, and then because it's in theory teleported down here, he's basically putting all those controlled operations that should belong to that part up here, putting them down there, and it doesn't kind of work right away. And so I think the issue here is that it's not you don't do that at the logical level. You don't do that to protect a particular state. You do that per qubit, like per physical qubit. And so you represent a logical qubit with 9 physical qubits that are entangled in such way. That's the way that's why I understand it. And I'm might be completely wrong, but that's the idea. Uh, yeah, so that's the idea basically. And so I went ahead and I found this in the Wikipedia. And so in the Wikipedia, you've got these in here. You've got like some sort of explanation. But you've got this in the Wikipedia here as well in the shape of a circuit. And oh, cool. And so what I'll do is I'll go ahead and build that because I think it can be interesting to basically analyze the behavior. I think basically what those things are doing in here, what those blocks are doing is the phase correction, and then I think just intuitively, and then these plus these, or in particular these, is doing the sort of the flip correction, the 0-1 correction. And the concept here is that it's going to basically correct based on what the majority of these three registers. If you think of these 3 registers, what the majority say, then this is going to be the value that's corrected towards, I think. So let's give it a try and let's play with this a little bit. I'm just gonna, I'm not aiming here at doing anything concrete, just playing with the circuit, seeing if I kind of, can understand this intuitively. So let's go ahead and build this. Let's see. What's the best way to do that? Maybe side by side. So we've got 2 control beats here. Then we need a. So we're gonna play with these and that way. Yeah, I think that's it. Then we've got Hadamard, we've got a Hadamard, we've got a not a Hadamard, and now we're doing more control bits in here. And so we're doing these and these. Now I don't want these to look like that, so that's definitely Gonna take some extra space, I think, here to make sure those things don't get connected where they shouldn't be connected. Exactly. And now basically we can apply in here the whatever error we want to simulate that's happening. So I'm gonna add maybe a bunch of these gates just to mark it, just so I know where this goes. So I'll just do something like this. Right? So this is where where this whole thing is supposed to be. Can I just I think I can copy that, so I'll just put it in the middle, right? For example, we'll say, I don't know, what happens if we've got a bit flip in here, right? So this would be simulating a bit flip error. Or what if I got like a Z flip, like a phase flip here, right? So that's the way that we're going to approach these. Let me get rid of these right now. So next is basically undoing, or not undoing that, but so these and these against these and these and these. Okay, so at this point I think I just need to make that a little bit bigger. And now we're gonna get the controls in here, connected in here. So this just gets like that, and then these guys go down here. And then we've got basically those go like this. And then we've basically got that kind of notion, okay, which is probably going to do the correction. That's the part that's correcting. So that definitely takes some extra space. What is these? Sticky keys. No, I don't want sticky keys. What are you doing? So we've got this one finally here. There's no way I think I can put those darkly below each other because they're just going to connect. So I gotta have it this way, sadly, which just makes the circuit a bit bigger than I'd like to. Then we've got a Hadamard. Then we've got a Hadamard in here. Then we've got another Hadamard in here, and then we've got another Hadamard in here. And at the end, basically, we need some stuff in here. Okay, so we need those other control nodes. Oh, stop all these sticky keys. Here and here, basically. I have the impression I know where this is going, but let's see. I think I got it right now. I think I got it right. So this shouldn't have affected anything. It's all zeros, right? If I, in theory, let me save that. I'll bookmark that into Shor error. Cool. In theory, let me just put that back in here. If that is a, if I now, whatever state I put in here should, not in here, sorry, in here, right, should kind of stay the same at the end here. So we're going to put a block sphere, because this is just for 1 qubit, okay? So block sphere, and also take a look at the amplitudes. And just so, we kind of get the phases in there. So, if it's a plus state, then we've got this, and then it's kind of, the same thing here, right? Now, let's play with these. So if I now, or maybe I would like to pack all this, but I don't want to pack it because I want to keep those control nodes and harmonics and whatnot visible, so I can sort of think about what the circuit is doing. But let's play with let's now simulate, for example, uh, a I don't know, a there's an error, right? And there's a bit flip in here. Cool. So it's kind of corrected, right? And again, remember, this is supposed to be like the idea here is you're not supposed to. This is not supposed to. You're not supposed to put a circuit now in here and do and this is kind of supposed to shield it or something. This is just to kind of error correct that qubit, that wire that we have here in the very top. So this is something that you don't do at the circuit level, at the logical level when you develop an algorithm. This is something that goes one level below in the stack, in the sense that this is something that the hardware does, right? So you would treat those 9 wires in here as one logical qubit. And so if you would want to implement an algorithm set, say for example quantum teleportation, that's one qubit for you. So you need these 9 qubits 2 more times, because quantum teleportation basically needs a what's it called? There was what's it, like 3 qubits, I think. Yeah. So and so you could of course then kind of maybe try to simulate that. I think I could do it with Quirk even. I think it supports up to 16 qubits, but that would be quite insane. And then you can think of, you know, how does a control knot look like, right? Like it's not that you can't just control knot here. Like you gotta, it's almost like you gotta control knot 3, like, I don't know if you would have to do this 3 times, like 1 per register, because I like to kind of think about these being, these being registers, like, this is, no, wrong. This being one register and this being another one, right? And so it's like, yeah, because inside each register, these additional 2 qubits seem to be responsible for phase corrections, I think. And then the fact that you're doing a control knot in here and in here, so you're basically entangling your state with this register, with this qubit, and with this qubit. And if you ignore everything that's happening in here, right? Let's ignore this for a second. That's really what's doing, what this portion of the circuit is doing, is saying, okay, so has anything changing here, right? So let's say if we got a plus state, right? The This is entangled. Yeah. So if we've got a plus state, right? This literally means that your amplitudes in here, take a look at the whole system, right? It's the, what's that state? So the all zeros, I'm trying to figure out it's complicated to see. What will be the state? Is it the state? Kind of, I think. But essentially, if you, I'm trying to reason about this intuitively. If you let's say it's a plus state in here, right? And so you're entangling it with these, and you're entangling it with this qubit. Mm, so what have you got as a state in there? You've got a um, so if you've got the plus state in here and you do these, you've got the state, this state, sorry, this state, 3 zeros and 3 ones, exactly. They all agree. And so if something in here in between happens, right? Like let's say like a bit flip in here, for example. The 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 error correction in here. So what was that? It was a thing like this, and then it was like that, and like that. That's not doing what I expected it to do, I think. Is it this way? Yeah. I'm trying to ignore the qubits in between. Bum, 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 bum. And this is the error we're simulating. So you're you wanna, what you wanna do is you wanna make sure that you correct that qubit. So you wanna still have a plus in here, which you kind of have, right? Like your block sphere. What if this is actually protecting you against the? No, that's not protecting. That must be these. I'm trying to think about a way to reason about it. So you entangle these, and then if something like this happens, the steel is gonna say, for uh, for the for the cases where we've got a one. Yeah, I can't reason about this in a smooth way. Give me a second. Uh, mm, because essentially it takes that state, right? And if it's maybe that's the wrong way to see it. Like let's have a simpler state. Let's have a one, right? So you've got a one, and you want to end up with a one at the end as well. But let's say that now something happens here, like a bit flip, right? That's maybe going to be easier to see this way than with the superposition state. So this one, what this will do is it will basically flip these two bit to qubits to one as well, right? So and then what's going to happen here is if there's a because let's assume that this gets flipped, then this is going to be now a zero, right? And so this zero makes these two gates, they don't take place, but then this last one basically self-corrects and puts it back to one. If we were going to do the opposite, say, this is a zero, right? And that flips it into a one. Well, then basically those two things trigger, and then again, that last Toffoli gate corrects it back again. So that's the mechanism. Now it works for all the other states because of the linearity of quantum computing. But I guess that's a lazy explanation of the whole thing because it's difficult to reason. It's really difficult to reason with superpositions in mind, honestly, because if this is let's even say this is the I state, right? So that's what you've got. and that's what you want to get at the end, right? So if this is the I state, right, what you're going to end up with, you need to take a look at the entire system, because now there is basically entanglement. So you can't easily take a look at this stuff. That video is turning to be a bit longer than expected, so I think I'll have to finish it in a second. But basically, that's what it does. So what this is doing, if you take a look at the amplitudes here before, it's moving that one all the way here to the 111s. It's encoding. So it's kind of attaching the 0 and the 1 component and the two ends of your superposition. So if now a bit flip happens, which would basically mean that the things get mirrored, you would still have. So what you still have now is the so how does this? So that self-correction happens in a similar fashion because you're okay. Let's put it this way. Yeah. It's doing these. It's really. So if nothing happens, let's say nothing happens. Here's where there happens. Nothing happens, then these things they just kind of reverse the thing and go back to that state basically, because that gate doesn't have any influence. So this is uncomputing literally. Maybe it will be easier to see it. Yeah, it's basically uncomputing. But if indeed something happens, right, then you're going to have that effect that this uncomputation is going to end up. It's going to end up down here. So it's, at the end of the day, but I still understand why this then in here and not in here, but still it's giving us the right blocks here. That's what I don't fully understand. But this is because it's tricky to reason with states in superposition. But okay, I'll turn that into, I guess, probably a couple more videos. But intuitively, I think that's what's happening. This portion, let me clean that up. So this portion here and here takes care of the bit flip, and these other ones in here take care of the phase flips. So we'll take a look at the phase flips in the next video probably, and then we'll just try to put everything together. But I just want to use as an exercise also to fine tune my way of reasoning with superpositions, because that's what's intuitively complicated. Because with the 1 and 0 case, it's obvious, it's easy because it's kind of more classical, right? Cool, that's it. It's just a short exercise. Nice, thank you.